All right, so we found out in our couple of lessons now that taking the natural log of both sides of an equation can help us simplify and then apply other rules to take some derivatives. So I know the lesson is about exponential functions other than base of e, but here's an example it's going to talk about something called log differentiation. So when you get questions that are really complicated, if you look at this question, you've got a product law in the top, you've got a quotient law, you've got a radical in here, and you've got something cubed. This is a beauty of a question, and you could go back and you could use all kinds of different rules: product rule, quotient rule, chain rule, find your answer. But we're gonna do something called log differentiation. We're going to take our equation, and what we're going to do is we're going to take the natural log of both sides. So we're going to use a little bit of math 30-1, where you recognize, again, that if you have a product, it means you write it as a sum of logarithms. And if you have a quotient, you write it as a difference. You subtract your logarithms. All right, so again, the layers are natural log of y and natural log of e to the x. We've got adding going on because this was a product. Natural log of x squared plus 1. I put the exponent of a half here, and subtract natural log of x squared plus 2 cubed. So that was kind of one layer. The next layer is that these exponents get to go in front of the log expression. So x goes with natural log of e. We'll talk about this one in a second. This 1/2 becomes the expression of natural log x squared plus 1, and this 3 becomes minus 3 natural log of x squared plus 2. Well, what we're doing here is we're using some more math 30, and when your bases are the same, the answer is the exponent. So remember, this is log of e to the base e. So these bases match up, so the answer is the exponent. So the answer here to this expression is just 1. So that's why when I write my question here, natural log of y, x, this is really 1x, right? Because this whole expression, natural log of e is 1, so this is 1x. And a half, natural log of x squared plus 1 minus 3 natural log of x squared plus 2, right? So our first step then, or our first steps, was all about changing this expression into a log expression. So very math 30-ish. Now we're going to do some calculus. Now we're going to do some math 31. How do you take the derivative of a log expression? It's the reciprocal of the function times by the derivative. So it's 1 over y dy dx. This is a sum and difference rule in here. This is not product rule, right? Because again, a half is just a stretch factor. 3 is just a stretch factor. So the derivative of x is 1. Derivative 1/2. Natural log. So the rule is reciprocal of 1 over x squared plus 1. And then what's the derivative of x squared plus 1? So that's the layer. When you look at cleaning this up, this 2x divided by 2, those 2's cancel out, and it's just x with x squared plus 1. Here you've got 1 over x squared plus 2, right? So reciprocal of the function, again, times by 2x. Nothing cancels out this time, so this is a 6x over x squared plus 2. And remember, when you have 1 over y on the left-hand side, it really just becomes y times the right-hand side. So same as we did, I guess, on our example number 1, where we talked about how do you take the derivative when you don't have base e. So I got this y value sitting here again, and remember what y was? Y was nothing more than this expression. So we're going to make sure we put that back into y. We're going to add some fractions. So you can do like math 20-1. You got to figure out the common denominator, right? So your common denominator is x squared plus 1 times x squared plus 2. You multiply x squared plus 1 times x squared plus 2 over x squared plus 1, x squared plus 2. This is missing the x squared plus 2 top and bottom. This is missing the x squared plus 1 top and bottom. So this is awesome, right? So we got some calculus happening here. All right, so we did some replacement. Now I want you to multiply this out and simplify it. So now we're doing math 10. Like I said, to me, this last lesson incorporates just tons and tons and tons of great math. Okay, so we've got the Math 30 rules with logarithms. We've got Math 20-1 rules with adding rational expressions. We've got Math 10 rules with simplifying polynomials. And now we're going to do some more Math 10 in a sense, because I've got x squared plus 2 cubed. I got x squared plus 2. I'm going to multiply with like bases, so I add the exponents. I've got x squared plus 1. I've got x squared plus 1. This square root means it's x squared plus 1 to the half. This is x squared plus 1 to the whole. So these cancel out and leave me a square root, or x squared plus 1 to the half in the bottom. So great. Just honestly, I think this is just a fabulous question, right? We got so many layers involved in it. So again, just a real quick repeat. When you've got a mess, when you've got a complicated situation, sometimes it's nice just to write it as sums and differences. Use your Math 30 skills, write things out. And then before you take the derivative, make sure you simplify as much as you can when you take your natural logarithms. Use the rules, use your Math 31. Derivatives are 1 over the function times the derivative function, 1 over the function times derivative function, 1 over the function times by the derivative function. Math 20-1, add rational expressions. Recognize what you need for a common denominator. Math 10, multiply and simplify. Math 10 or Math 20, right? Like bases, do your exponent rules. Great question. Okay, let's do one more example in this video, and then we'll do one last example. So here again, same kind of idea in question 3a. This question does not have to be log differentiation. This would actually be a fairly easy product rule to do. So you would have done a question like this back in chapter 2. We want to show you how it looks though when you use log differentiation. All right, so again, Math 30. Take the log of both sides. This is a product, so it's going to be adding between. The exponent of 4 goes to the front, so it's 4 natural log x squared plus 1. Exponent of 3, 3 natural log x cubed plus 2x squared. All right, so we got this all in red here is just taking the natural log of both sides. One of the things that's maybe not the best in this question is you got x cubed and x squared in the same term. We could have done some common factoring early in this question and probably saved yourself some grief, but we're going to work it out like we didn't know we could do that. Derivative, all right, 1 over y times by the derivative of y. X squared plus 1, so it's 4 times 1 over x squared plus 1 times by 2x. The 3, right, is what the original function was again. X cubed is 3x squared plus 4x. So what I did here with this 3x squared plus 4x is that I factored the x out of 3x squared plus 4x, so it's x times 3x plus 4. I factored x squared out of my denominator, so it's x squared times x plus 2, just to show that there's a common x in the numerator that can cancel out an x in the denominator. Should have done it sooner in the question, but we didn't, so it ends up being a bit messy. Put the y value back in. So the y value was x squared plus 1 to the 4th, x cubed plus 2x squared cubed. All right, so again, if you look at this, x squared plus 2x, if I factor the x squared out, it's x squared times x plus 2, all cubed. So I'm going to use that down here. X squared cubed is x to the 6th, x plus 2 cubed. All right, so probably should have started with 3 things in the product instead of 2 things in the product. Would have saved myself a whole bunch of grief later on. A little bit of Math 20-1 happening in here. I want to add my terms together. I've got x squared plus 1, and I've got x with x plus 2. So I'm going to find my common denominator. So I've got my x, I've got my x squared plus 1, and I've got my x plus 2. So again, a little bit of Math 20-1, multiply this together. 8x cubed, 16x squared. Multiply these 2 binomials together. Gather up your like terms, right? 9x cubed, 12x squared, 9x, and 12, blah, blah, blah. Make everything look pretty. And then how do you simplify? An x to the 6th with an x. So that becomes x to the 5th. X squared plus 1 to the 4th, x squared plus 1 to the 1. So that's x squared plus 1 cubed. X plus 2 cubed, x plus 2 becomes x plus 2 squared. And then simplify what's in the numerator. All right, so that's another example then. Again, this is a question that didn't need to be log differentiation. Maybe it was easier, maybe it wasn't. I think part of the problem was that we started a question that had that common factor to begin with, And if we would have started with 3 things being multiplied instead of 2 things being multiplied, life might have been a lot easier. But anyways, lots of good math on that one as well. Lots of math 20-1 really in the end. So, okay, let's shut down this video, and we'll do one last video with our last example coming up here.